When we think of compute, we think of ones and zeros. And those ones and zeros are basically electron potentials in a computer chip. It wasn't always working this way, and for sure it won't be the case in the future. In this video, I want to explore 5, in a way, exotic types of compute, which one day will replace our traditional computers and definitely outperform it. Over the last 100 years, we went from mechanical computers to punch cards and then to the digital vacuum tubes. And eventually, in 1946, the first electrical computer, so-called ENIAC, was released. It contained 18,000 vacuum tubes and occupied the entire room. This machine consumed enough energy to power a small town, so it was quite a monster. At the time, vacuum tubes were for sure a leap, but even economically, it was clear that such a machine simply cannot scale further. Until 1947, when the first silicon transistor was invented at Bell Labs. Probably this was the most important invention of 20th century. With the advent of transistors, digital computers just took off, and ever since the compute scaled exponentially. Nowadays, practically every computer we use is digital, so it's all about electrons moving in silicon. And before we start with the list, just keep in mind that some of the mainstream technologies of today, at some point of time, were just a product of science fiction. So, what future brings us? The first technology which offers a paradigm shift in compute is photonics. The main idea is to use light for compute. Just imagine, microchips of the future will run on light. And many people are heavily betting on this technology. Why? Because it actually resolves all the key bottlenecks of the modern compute. And it all starts with artificial intelligence. The size of neural network models is constantly increasing. Let's take, for instance, GPT-3, which is a natural language processing model. It has 175 billion parameters. And GPT-4, which will be released very soon, will have 100 trillion parameters. Just to give you a feeling, training of GPT-3 requires about the same amount of power as powering 100 houses for over a year. AI applications demand much more compute, and our traditional compute simply doesn't scale as fast and as efficient. And you know what? By using different physics, in this case light, we can come around all these bottlenecks. And the key feature of light that we can parallelize compute in the frequency domain. And this is huge for AI. And this is only possible because light has an amazing property of having many different colors which do not interfere. Actually, we encode neural network information at each color, at each wavelength of light. And then we compute at all the colors of the light simultaneously. And that's actually very fast. It's the speed of light. I have a separate video explaining how it works. Check it out later because it's magic. No surprise that many people are believing in the bright future of photonics. There are already photonic chips on the market. For instance, Mars photonic chip by Lightmatter. Lightmatter is a startup born in MIT. They leverage lasers and silicon photonics to do core computations for AI and deep learning. Deep learning is all built around linear algebra, multiply and add operations. And they realize these operations using silicon photonics. This provides huge benefits in terms of efficiency and of course enables massive parallelism. If you take any of the standard neural networks, Lightmatter chip will be at least 10 times faster than NVIDIA 800 GPU. And actually compute with light requires less power than controlling electrons in transistors. Apart from Mars chip, there is a bunch of other cool photonic startups like Silence Labs. They've implemented photonic in-memory compute. I also have a video about them. May check it out later. Now, when I first heard about the whole concept of computing with light, I was thinking, why can't we do the same with the RF wave, radio frequency waves, which we use for 5G, so for communication, right? And in fact, we can, because I found already a bunch of publications about this. Both radio waves and light are basically electromagnetic waves. The main difference is just in their frequency, and we can actually apply exactly the same principles for compute here. In terms of technology, RF will be definitely much cheaper than optics because it's widely used for communication. The disadvantage is that there is less spectrum available. While light has terahertz spectrum, RF waves have gigahertz spectrum. This practically means that we can parallelize much more with light because we will have like 1,000 times more carriers which do not interfere. While many people are betting on photonics, on photonic chips, and there are already many commercial chips on the market, RF compute is still just research. I found a couple of papers. If you're interested, I will link it below. The third way to compute is biological, actually putting a brain in a dish. I have to warn you, it's quite controversial. The idea is to use live human neurons for compute power. It's actually the original idea from the Matrix, that machines use humans for compute power. And the Matrix is just a part of a software interface to the brain. This was the original script, but then it was decided that the average audience at this time wouldn't understand it, and the idea was scrapped. And now it turns out it's possible. So there is a startup in Australia who are actually growing live human neurons and then integrating it in a traditional computer chips. So literally putting man's mind into machine in order to advance AI. The startup is called Cortical Labs. Why this approach is so efficient for AI? Because neurons, these are real brain cells. It means they can learn, they can grow, replicate, or even die in response to the environment. And it works because both electrical and biological parts can interface each other because they both communicate with the electrical pulses, so with electricity. The company's first proof of concept is to train the brain in a dish to play Pong. Neurons live in the game, and they are being constantly stimulated from outside.
Every time the ball reaches the goal area, we give the neurons a reward or punishment stimulus based on whether the paddle intercepted or missed the ball. This happens roughly once every 2 seconds.
So in terms of gameplay, what we do is that we feed in the state of the game, and then after a certain length of time, if the neurons don't do what we want them to do, which is in this case move the paddle to intercept the ball, then we punish them in some way. The most efficient way of punishing them is, surprisingly enough, just silence. So we essentially just cut them off completely from the game world. We just put them in a dark room if they completely misbehave and don't act the way we want them to do, and then the next time we find that there is actually an improvement of the play.
Biological compute is very low power because actual neurons doing the job. Just think about it. Our brain features 86 billion neurons, and our level of intelligence runs at just 20 watts of power. This is the power consumption of a light bulb. The human brain, with its trillion neuron connections, is capable of making 15 quintillion operations per second. As of today, it might be only matched by massive, huge supercomputers burning lots of energy. Another advantage of this technology is fluid intelligence. It means they can adapt to environment in real time. It can restructure and reorganize itself. It is essential for any kind of AI applications like robotics to adapt to the real-world environment quickly. When we talk about compute, we typically mean digital, so information will be encoded in a binary fashion, zeros and ones, and there is nothing in between. While there is actually another way to compute, analog. Analog means continuous, so you're not only having zeros and ones, but all the values in between, just like in real world, because the real world is analog. We are analog. Analog compute is not a new thing. For many years, analog computers were only the one we had. We used it to predict weather, eclipses, and even the first AI chip was analog. Back in 1958, Frank Rosenblatt built a perceptron, a computer designed to mimic how our brain works, how neurons fire in our brain. According to Rosenblatt, it is capable of distinguishing between cats and dogs, woman and man. Overall, it seemed to be a machine capable of original thought. While in reality, it didn't really work, and it was heavily criticized for it. And eventually this led to the first dark period of AI, so-called first AI winter. And now, guess what? We may see a comeback of analog computers. compute, particularly for AI, because analog seems to be the best fit for AI inference applications. The key idea is to encode the neural network weights into the resistors and then perform compute using voltages and currents. And the advantage of this is that we can perform compute massively in parallel in the fraction of time and power. Actually, IBM is already working on such an analog chip for AI. On top of that, there is a bunch of cool startups like Analog Inference and Mythic. And Mythic has built the first commercial analog chip for AI. And with that chip, they were able to achieve the performance of a similar digital chip at about 10th of power. And it's like 30 times cheaper. However, analog compute has one key drawback. It's not as precise as digital. And that's because when we manufacture analog chips, we will be always getting the mismatches in components like resistors, capacitors, and this will result in an error. We can expect about 1% error. Good news that for this particular application, so for AI compute, we don't need that high precision, which means with the ever-increasing demand for AI, we may now see the comeback of analog compute. At the same time, many people see quantum computing as the future of computing. Quantum computing uses qubits, which can be both 0 and 1 simultaneously. And this feature allows to perform many calculations in parallel. And this is what we want. You know, with 50 entangled qubits, we have already more states than any possible supercomputer, meaning that we can demonstrate quantum supremacy over traditional computers. With 1,000 qubits, you can solve quantum chemistry and address quantum neural networks. And let's say with 1 million qubits, you can do cryptography, unstructured search, and any sort of magic. There are different types of qubits, but the most popular is a so-called superconducting qubit. And the main issue with this one is integration, because the qubit itself is relatively large, and also you always need a simulation and a readout interface, so you have lots of wires. Here you can see a setup by Google, which was used to control 50 qubits. This is obviously very challenging to scale. IBM has recently presented their 127 qubits Eagle quantum processor, while the famous D-Wave has already about 5,000 qubits in their Pegasus supercomputer. Yes, maybe hundreds or a couple of thousands qubits will work. But what is next? Because the key challenge of this approach was always to integrate more qubits to make it somehow practical. You know, there is actually a very exciting and interesting alternative to superconducting qubit, so-called silicon quantum dot. As you may guess from the name, it's based on silicon. So it's leveraging standard silicon CMOS technology to implement qubits. It's basically like a transistor, where you isolate just one single electron, and then you get two levels, spin up and spin down. As you know, the silicon technology, we were able to achieve really good scaling and really good integration. This means we can integrate millions of silicon qubits on a single chip. I do believe in the silicon quantum dot future of quantum computers, because when they are able to solve the problem of error correction, they've already got a 1 million qubit quantum computer. And I'm really excited about this because there is a lot of potential for quantum computers, especially in such hot topics like drug discovery and climate change, and it will just make this world a better place. This is what all of us trying to do here. At the moment, all of these different flavors of compute is still a niche, and the main application is artificial intelligence. Because AI field is very demanding right now, and we need to find a way to scale out efficiently for the same task, multiply accumulate operation. The ongoing trend in AI that models are getting larger and larger. So whatever scales out better in terms of parallelism wins. But if we want to substitute the compute as it's of today, we need to think of general purpose compute and about the economy of scale. It means this compute has to be cheap, scalable, and be able to do everything. You and me, we are so lucky to live in the era of fast technological progress, and I'm really looking forward to see where our ideas will bring us. And especially I'm curious to see which impact AI will make on the world, let's say in 20 years from now. Let me know what you think in the comments. If If you want to support me creating these videos, the link to the Patreon is below. And now I have a Deep on Tech newsletter. You can subscribe. Also, the link is below. Thanks for watching, guys. I will see you in the next video. Ciao!